Hi and Assalamualaikum everyone. Today I would like to introduce to you guys about what is the second law of thermodynamics. So the second law of thermodynamics is used to identify the direction of process and also asserts that energy has quality and also quantity. Energy will flow in the direction of the high quality to a lower quality, and the second law is also used to determine whether the process is spontaneous or not. So let's consider an example. Here is the situation where two gases are mixed together from 1 to 2. So the process occurs spontaneously, but if it is in the reverse direction, will the mixed gas become unmixed spontaneously without external aid? In the first law, the process can occur in the reverse direction because energy is the same. So we need the second law of thermodynamics to govern the direction of the process. This law states that any spontaneously occurring process will lead to an escalation in the entropy of the universe, which explains that isolated system entropy will never decrease over time. So in some cases where the system in thermodynamic equilibrium or going through reversible process, the total entropy of a system and surrounding will remain constant. An example of reversible process would be like forcing a flow through a constricted pipe, which as the flow moves through the constriction, the pressure, the temperature and also the velocity will change, but the variables will return to its original value downstream of the constriction. So the state of the gas will return to its original condition and the change of entropy of the system will be zero. So if the physical process is irreversible, the entropy of the system and the environment must increase and the final entropy will be greater than the initial entropy. So that is the introduction for the second law of thermodynamics.
So the second law of thermodynamics suggests that a hypothetical body with a large thermal energy capacity can be supplied and absorbed due to a finite amount of heat without causing a temperature change, and this is known as a thermal energy reservoir. Large bodies of water as ocean, lakes, rivers, atmospheric air can be accurately modeled as a thermal energy reservoir, and this is due to the thermal energy storage capabilities. For example, the atmosphere doesn't warm up due to heat loss from residential building or waste energy power plants. Two-phase system and industrial furnaces can be modeled as reservoir due to their ability to absorb and release large amounts of heat while maintaining constant temperature, and then this system with their controlled temperature can supply a large amount of quantities of thermal energy as heat. A body can be considered as a reservoir if its thermal energy capacity is large relative to its energy supply or absorption. And for instance, the air in a room can be modeled as reservoir in heat dissipation analysis from a TV set, as the heat transfer is not significant enough to affect the room air temperature. Source is a reservoir that supplies heat, while a sink is one that absorbs heat. Thermal energy reservoir, also known as a heat reservoir, and are crucial for energy storage. Heat transfer from industrial sources to the environment is of major concern to environment as well as to engineers. Irresponsible management to waste energy can significantly increase the temperature of portion of the environment and causing what is called thermal pollution. And if it is not carefully controlled, thermal pollution can be seriously disrupted marine life and lakes and rivers. However, by careful design and management, the waste energy dumped into large bodies of water can be used to improve the quality of marine life by keeping the local temperature increases within safe and desirable level. Thank you.
As we may know, it's relatively easy to transform the mechanical energy into thermal energy. And for such an example, rubbing your own hands. So by rubbing your own hands, you are transforming the mechanical energy that's stored in the motion of your hands into thermal energy. So by time, the temperature of your hand or your palm will increase because of the increasing of internal energy. So I have a question. Can we reverse the process, or can we transform the thermal energy into mechanical energy? And yes, we can do that by using a device known as the heat engine. The main idea behind the heat engine is to transform the thermal energy into mechanical energy under one condition: if the energy that transforming is from a higher temperature system to a lower temperature system, or from a hot object to a cold object. And to explain that more, I would like to. As we can see from the following diagram, we have energy that transformed from a high temperature source to a low temperature sink. And while that energy is transforming from a high temperature source to a low temperature sink, it will produce work. So that is the simple diagram to show the process of transforming a thermal energy into mechanical energy using a heat engine, and to determine the work, or as given in the diagram, W equal Q in minus Q out, which is the amount of energy from a high temperature source minus the amount of energy from a low temperature sink.
Now, let's talk about thermal efficiency. The thermal energy produced from the combustion of fuel-air mixture is transformed into mechanical energy, which moves the car. However, not all thermal energy is converted into useful work. This thermal energy which is not converted to useful work is called waste heat, which is Q out. This heat losses is unavoidable and greatly limit the efficiency of heat engine. For example, the engines of a car are only 30% efficient. This means that for every 100 joule of thermal energy produced by the combustion of gasoline, only 30 joule are used to move the car. Therefore, it is impossible to construct a heat engine that is 100% efficient, which can fully convert all the heat into a useful work. An engine that converts energy into more work and less weight is said to be more efficient. Now let us have the equation of efficiency. It is calculated as efficiency equal work done divided by input heat times 100%. But since work is just the input heat minus the exhaust heat, the equation becomes efficiency equal the input heat minus the exhaust heat divided by the input heat times 100%. Simplifying this equation, we have input heat divided by input heat, that is 1, and we have the remaining minus exhaust heat divided by input heat times 100%, where Q sub I is the energy removed by heat or energy in cold reservoir, and Q sub H is the energy added by heat or energy in hot reservoir. To understand more about how to use this equation, there will be example question at the end of this video.
So next, we're gonna talk about, can we save Q out? Before we go further to our topic, which is can we save Q out, we have to know the definition of the Q out itself. Q out defined as the magnitude of the energy waste in order to complete the cycle. Basically, Q out is amount of heat rejected from steam in condenser to a low temperature sink, for example, atmosphere and river. Alright, now let's get back to our question. Can we actually save all the excess heat or Q out that had been rejected to the atmosphere or river throughout the process? Well, unfortunately, we cannot save the Q out or the heat that have been rejected through the atmosphere or river. This is because of without a heat rejection process in a condenser or in a heat engine, this cycle cannot be completed. Cyclic devices such as steam power plants cannot run continuously unless the cycle is complete.
It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce an equivalent amount of work. In simple terms, this statement implies that it's not feasible to create a continuous cyclic process that solely extracts heat from a single source and converts it entirely into work without any other effect. This principle is deeply rooted in the concept of entropy. Entropy is a measure of the unavailability of a system's energy to do work. When heat flows from a hot reservoir to a colder one, entropy increases. According to the Kelvin-Planck statement, it's not possible to take all the heat from a single source and convert it completely into work without affecting the system's entropy or involving another heat reservoir. In a practical terms, this means that perfect efficiency in a cyclic process using only one heat reservoir is impossible. Some energy will always be lost in the form of heat and entropy will increase, preventing the conversion of all supplied heat into useful work. This statement is crucial in understanding the limitation of heat engines and energy conversion processes, as it sets a boundary on the efficiency of such systems, stating that they cannot achieve complete conversion of heat into work in a cyclic process without additional effects or multiple heat reservoirs.
Alright, I will show you guys the example question from this chapter, which is 6.3. So let's do now. So for the example 6.1, net power production of a heat engine. The questions need the net power output and also the thermal efficiency. So to determine the net power output, we have to know the 80 megawatt is the the output rate of heat. So this is the output and this is the input. So we use this formula. Okay, so this is the output, this is the input. So to use this formula, which is the net power output, so the power output formula is come from this formula, which is work over time, is equal to the output rate of heat minus the input rate of heat. So 80 minus 50, we get 30 megawatt. The next question is the thermal efficiency. So easily from this formula, we get the thermal efficiency, which is the net power output that we get from this question, the 30 megawatt, divide over the output rate of heat, which is the 80 megawatt, and then we get 0.375, or in percent, we got 37.5. Okay, so this is for the first questions. And then moving on to the second question, which is fuel consumption rate of a car. A car engine with a power output of 65 horsepower has a thermal efficiency of 24%. So this is the thermal efficiency. 65 horsepower is the output rate. The output work rate, which is the power output. So determine the fuel consumption rate of this car if the fuel has a heating value of 19,000 BTU over LBM. So to get the fuel consumption rate, we have to get first the output rate of heat. So from this formula, we rearrange the formula and we get the output rate of heat. And then to get the output rate of heat, we have to first divide the power output over the thermal efficiency. But this is in a horsepower unit, so we have to convert it to British thermal unit. We get 689,270 British thermal unit per hour. And then from this value, we want to get the rate, the mass flow rate. So divide with the 19,000 British thermal unit over LBM, and then the last answer unit is in the LBM per hour, which is we get 36.3. Okay, that's all.